If you lie back for a moment and imagine yourself shrinking, not metaphorically but literally, you might picture the familiar world dissolving around you. First the room, then the dust on your desk, then the molecules inside that dust. Layers peel away like pages drifting off a book. You descend past atoms, past electrons, deep into a realm where nothing is smooth and nothing stands still. There is no wind on your skin, no sound in your ears, only the silent hum of distances collapsing faster than your breath can follow. It is a strange kind of falling, gentle quiet, and infinitely deep. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. You pass the scale of an atom 100 million times smaller than the width of a single strand of hair. Then you drift inward to the nucleus, tiny, hard, and so dense that most of the atom feels like empty sky. Smaller still into the realm of quarks, the jittering points inside protons and neutrons. And for a moment it feels as though you could continue forever, as if the universe will keep offering smaller and smaller secrets as long as you're willing to look. But then just as the world seems poised to reveal one more layer, everything begins to blur. Your vision, so crisp at first, softens around the edges. Shapes lose their meaning. Distances become indistinct as though reality itself is running out of resolution. You've arrived at a frontier once so deep that the very idea of zooming in stops behaving the way we expect. At around 1.6 guesses 10^35 meters a scale called the Planck length, the universe no longer guarantees a coherent answer to the question, what lies beneath our best theories begin to disagree. Space-time and energy start flickering like static on an old television. It's a strangely peaceful boundary, silent yet impossible to cross. A limit woven not from matter but from the laws themselves. To understand why this happens, we have to revisit a simple rule that has guided every microscopic discovery humanity has ever made. To see smaller things, you need shorter wavelengths, and shorter wavelengths demand higher energy. This rule has shaped science for centuries. Every major leap in our ability to observe the microscopic world, from the first glass lenses to modern electron microscopes and particle accelerators, has been built on the same principle. When we first invented optical microscopes, we illuminated cells and tiny organisms using visible light. But visible light has wavelengths hundreds of nanometers long, far wider than the size of an atom. So even the finest lenses could only show us structures much larger than the atoms that make them. It wasn't a matter of poor craftsmanship or lack of imagination. The waves were simply too large to reveal the details. Like trying to find the grain of a wooden table using a brush swept with broad flowing strokes, you could feel the surface but never the subtle patterns beneath. So scientists turned to something more subtle than light electrons. As waves, electrons could be tuned to much shorter wavelengths simply by accelerating them. This was the breakthrough behind the electron microscope. When Ernst Ruska built the first one in 1931, he effectively created a new form of sight, a way to peel back the invisible with beams of matter instead of beams of light. And suddenly structures that had been hidden since the dawn of biology came into view: viruses, cell membranes, crystalline arrangements that once lay beyond imagination. But this shift from light to electrons didn't just give us sharper images, it pulled us deeper into a pattern. Every time we want to see smaller scales, we must inject more energy into the probe, doing the seeing. And this connection resolution through energy isn't a technological choice, it's a law of nature. This is where the story begins to curve. Because while adding energy helps us see smaller things, it carries a cost. Energy is not just a tool, it is also a weight. According to Einstein, energy and mass are two forms of the same thing. When you concentrate energy in a tiny region of space, you curve space-time around it. A little curve does no harm. But keep increasing the energy, keep forcing your microscope to peer into smaller and smaller targets, and that curvature grows stronger, denser, tighter. Eventually, the energy becomes so intense that the region you're trying to observe collapses under its own gravitational pressure. It forms a tiny black hole. The very act of looking too closely makes the universe turn itself opaque. Instead of revealing its secrets, it draws a gravitational curtain across them. This is the quiet paradox. Physics discovered the smallest layers of reality can't be seen by simply pouring more energy into a microscope. There is a point where looking harder makes everything disappear. That point, the Planck length, is not just a measurement. It is the edge of the map. And what lies beyond that edge we don't know. Not because humanity lacks better machines, but because the universe refuses to define those distances in any meaningful way. Below that scale, our equations predict chaos space, twisting time, fluctuating particles and forces appearing and dissolving so quickly that the idea of structure becomes meaningless. It's not a wall we can break, it's a boundary carved into the laws themselves. Tonight we will explore this boundary with calm precision, not as a cliff where the known drops into the unknown, but as a quiet horizon where the universe whispers its deepest riddles. You're invited to settle in, breathe softly, and let curiosity stay awake while your body rests. And if this calm corner of the universe feels like a place worth returning to, a gentle tap on like or subscribe is more than a gesture. It's a warm reminder that minds like yours still listen, still wonder. So now we drift into this first question. What truly breaks when we try to see smaller? And why is there a scale where the universe stops giving answers and starts giving silence? To see smaller, burn brighter. If you close your eyes for a moment and imagine holding a ruler in the dark, you can almost feel the scale of the world in your hands, the neat spacing of millimeters, the comfort of numbers that stay steady no matter how closely you look. But in the microscopic world, rulers don't work the way we expect. They don't shrink forever. They don't glide effortlessly into smaller and smaller spaces. Instead, measurement itself becomes a kind of dance choreographed, not by wood or metal, but by waves' ripples that define what can be seen and what must remain hidden. Every wave in nature, whether it's a vibration of air, a ripple on water, or a beam of light, shares one fundamental property: it cannot reveal details smaller than its own wavelength. The wavelength is the size of the wave's footprint, the distance between one crest and the next. If the thing you're trying to observe is smaller than that footprint, the wave simply washes over it without noticing anything at all. Think of tossing pebbles into a lake at night. Large, slow ripples move across the surface with elegant calm. If you placed a tiny grain of sand below the surface, those broad ripples would glide right over it, their shapes too gentle and too wide to sense something so delicate. To detect smaller features, you would need smaller ripples, tighter, sharper waves. This is the rule the universe quietly enforces. To see smaller, you must use shorter wavelengths, and shorter wavelengths always mean higher energy. Visible light, the rainbow we evolved to see, has wavelengths ranging from roughly 400 to 700 nanometers. In everyday life, that seems unimaginably small, but compared to the delicate structures inside matter, it is enormous. An atom is about 0.1 nanometers wide. That means visible light is roughly 1,000 times too large to detect it. When we shine light at an atom, the waves spread over it like fog passing over a pebble. The details vanish because the wave is too big to care. This is why no optical microscope, no matter how perfect its lenses, can show us an atom. The tools are not at fault. The limitation is built into the physics of light itself. Early scientists felt this limitation long before they understood it. No matter how much they polished their glass lenses or how cleverly they shaped them, the image always hit a wall. Cells, bacteria, fibers, they could see these things. They could marvel at the shapes of pollen grains and the legs of tiny mites. But the level below that, the realm of molecules and atoms, remained stubbornly blurred, like trying to read the finest handwriting using waves drawn across a swimming pool. If you've ever watched sunlight shimmer on water, you know how waves can hide more than they reveal. At the surface, the image dances beautifully, but beneath the details fade. The ripples don't focus, they don't sharpen, they smear. The same is true of light. But the story doesn't end there. Humanity is restless. When we hit a wall, we build a doorway, and in the early 20th century, physicists realized something astonishing. If everything with waves is limited by wavelength, then maybe we should use something with a smaller wave. Something more subtle than light. Electrons. Electrons, for all their particle-like behavior in daily life, also move as waves, and those waves can be made incredibly small, far smaller than the wavelengths of visible light, simply by accelerating the electrons to higher speeds. The faster an electron moves, the tighter its wave becomes. This meant that for the first time in history, we had found a wave capable of slipping into the hidden architecture of matter. But that step toward electrons, the idea of replacing light, the messenger of all human vision with streams of charged particles, wasn't a trivial leap. It required an entirely new way of seeing, a new form of imagination. Because in our minds, light is vision. It illuminates, it reveals, it carries shape and color into our eyes. But nature doesn't prefer light for vision. We do. And when our eyes and our lenses reached their limit, nature gently nudged us toward another tool. This transition from glass and light to electrons and magnetism is one of the quiet revolutions of science. It changed not just what we could see, but what we believed seeing meant. It showed us that the universe is not limited by our senses. We are. As you drift in this thought, imagine again those ripples in a pool. Wide, slow waves that gloss over pebbles. Now picture tapping the water more sharply, sending out tight, crisp ripples that touch even the smallest grains at the bottom. That is the shift from light to electrons, from the gentle waves of the visible world to the tiny ripples that can trace the outlines of atoms themselves. And so as scientists pushed deeper, they discovered a new truth to peer into the small. You must use energy as your light energy shaped into waves, so fine they can slip between the cracks of matter. But this story, like all good stories, has its own twist. As we add energy, as we push wavelengths shorter, we begin not only to illuminate the microscopic world, we begin to alter it. And the next part of our journey begins with that realization that the waves of matter reveal the world using their own rhythm, their own subtle geometry. That to see deeper, you must not just brighten the light, you must transform it. The next step takes us to the invention of the electron microscope, the moment humanity built a new kind of eye, one not made of glass but of beams, fields and moving waves, when matter becomes light. Electron waves. There is a moment in the history of science when reality itself seemed to hesitate as if unsure which face to show us. A moment when something we had always believed to be solid and definite, a particle suddenly revealed it could move like a wave, shimmer like light, and carry within it the power to illuminate worlds hidden far below the reach of glass and sunlight. That moment began with a simple but radical idea. In 1924, a young French physicist named Louis de Broglie asked a question that sounded almost like a riddle. If light can sometimes behave like particles, what if particles can sometimes behave like waves? This wasn't a metaphor. De Broglie proposed that every moving particle, electrons, atoms, even entire molecules, carries a wavelength one determined by its momentum. Slow particles have long waves. Fast particles have tight compressed waves. And if those waves could interfere or diffract the way light does, then matter itself might ripple and shimmer when pushed through the right conditions. At the time, physics was already swirling with strange discoveries. Light had shown itself to behave both as a wave and as a particle. Quantum theory was rewriting the rules of energy and motion, and yet de Broglie's idea still startled the scientific world. What does it even mean for the electron, the tiny building block of electricity, to have a wavelength? Nature answered that question just 3 years later. At Bell Laboratories in 1927, Clinton Davison and Lester Germer were studying how electrons bounced off the surface of a nickel crystal. They weren't searching for wave behavior, they were simply investigating scattering patterns. But the results took an unexpected turn. Instead of acting like tiny metal pellets, the electrons diffracted, bending and fanning out in the same elegant arcs, seen when light passes through a grating. Electrons were not simply bouncing. They were interfering, creating bright and dark patches, exactly like waves of water crossing over one another. In that moment, de Broglie's idea leapt from theory into reality. Matter waves were real. Electrons, those tangible, almost intuitive particles, were carrying wavelengths like light, and those wavelengths could be shaped, tuned, and focused. This single experiment cracked open a new world. Because if electrons could act like waves, then perhaps they could do more than scatter. Perhaps they could be guided, concentrated, and formed into a beam capable of revealing details far too small for visible light. After all, a particle accelerated to high speeds has a very short wavelength, and short wavelengths, as we learned, are the key to clarity in the microscopic world. This is where Ernst Ruska enters the story. In 1931, working in Berlin, Ruska built something no one had ever seen before, the first electron microscope. It wasn't elegant by modern standards, a modest device of coils, glass and metal, but it held within it a revolutionary idea. Instead of bending light with glass lenses, Ruska used magnetic fields to bend beams of electrons. Instead of depending on wavelengths measured in hundreds of nanometers, he relied on wavelengths thousands of times smaller created by accelerating electrons through electric fields. The result? Suddenly the microworld stretched open, cells sharpened, organelles appeared, crystals revealed patterns that had only been guessed at. Things that had lived in pure theory came into focus with shadows and edges. and as the technology improved, viruses once invisible to every lens humanity had ever crafted stood exposed like tiny lunar landscapes. Ruska had built not just a microscope but a new way of seeing, a way in which matter itself becomes the light needed to illuminate matter. There is a quiet poetry in this. To look deeper into the world, we had to abandon the wave of light and embrace the wave of the electron, the very substance of atoms. It's as if nature offered us a gentle hint: to understand matter, you must use matter's own rhythm, its own hidden geometry. Electron waves don't just strike a surface, they feel it. Their wavelengths probe the tiny distances between atoms, their phases twist through crystal grids, and their subtle interferences carry information that glass could never touch. And the faster we accelerate them, the tighter their waves become. The sharper the focus, the smaller the details they can reveal. By the late 20th century, electron microscopes evolved into towering humming giants, tubes of vacuum cascades of electromagnetic lenses, and detectors sensitive enough to read the whisper of a single electron's path. Modern transmission electron microscopes can now resolve distances smaller than 1/10 of a nanometer, letting us see individual columns of atoms inside a crystal, the precise arrangement of molecules, the slow drift of defects and dislocations that give materials their strength and weakness. In these images, atoms look like constellations, clusters of brightness, ordered, trembling, alive. When you look at such a picture, it's easy to forget what makes it possible: electrons accelerated to such high speeds that their wavelengths shrink into the domain of matter itself. Beams so fine they can pass between atomic layers like threads sliding between threads. But beneath the technology, beneath the steel and the magnets, the story returns to that original twist. Matter must become wave to reveal the structure of matter. Electrons, which build the world, must blur into vibration to show us the world they build. It's a quiet, profound symmetry, and yet even electron waves so small, so sharp, cannot reveal everything. Because beyond the atom, beyond the nucleus, beyond the quarks and gluons we will soon explore, lies a frontier where even these waves begin to falter. A place where the energy needed to make their wavelengths shorter bends space itself. But before we reach that limit, before we meet the strange creatures inside the proton, we must follow the next clue in the journey inward. The moment physicists asked not just whether matter was wave-like, but whether the nucleus, the heart of the atom, was solid at all. Why light can't see atoms, but electrons can. If you imagine holding a flashlight in a dark room, you can almost feel the way light touches objects, bouncing off surfaces, tracing edges, carrying shapes toward your eyes. Light is our most familiar messenger. It tells us where things are, it paints the world in color, it gives texture to every waking moment. So it feels natural to assume that if we want to see something smaller, much smaller, we should simply shine a brighter, sharper beam of light at it. But nature has its own quiet rules, and one of them is this: light cannot see atoms. Not because our instruments are weak or our eyes limited, but because the waves themselves are too large to notice something so small. Visible light has wavelengths between roughly 400 and 700 nanometers. That sounds tiny until you compare it to a hydrogen atom, which measures about 0.1 nanometers across. In those proportions, visible light is like trying to detect the lines of a fingerprint by rolling a yoga ball across it. The wave is simply too broad. It flows over the atom barely disturbed, like a slow ocean swell, passing over a single grain of sand. This is why optical microscopes, even the most perfect ones humans can build, are blind to atoms. The limitation isn't mechanical. It's woven into the physics of waves. But scientists, curious and stubborn, looked for a loophole, and they found one not by replacing light, but by using a different kind of light: X-rays. X-rays have far shorter wavelengths, around 0.1 to 10 nanometers range, small enough to interact with the spacing between atoms. Their ripples are tight and sharp, capable of weaving through the tiny gaps inside crystals and bouncing off the periodic lattice of atoms like sound waves reflecting down a narrow hallway. This shift using X-rays instead of visible light opened a door to a profound discovery. In 1912, the physicist Max von Laue directed a beam of X-rays through a crystal of copper sulfate. On a photographic plate behind the crystal, a pattern of bright spots appeared, dots arranged in an orderly symmetry. It was a cosmic fingerprint, a silent message from the atomic world. The X-rays had scattered off the atoms in the crystal, creating an interference pattern. From this, Laue realized something revolutionary: atoms in crystals form regular repeating structures, and the X-ray diffraction pattern was their signature. This experiment didn't just reveal atomic spacing, it birthed crystallography, a field that would later map DNA, proteins, minerals, and the deepest architectures of matter. And yet X-rays came with a price. They were powerful sometimes, too powerful. To produce waves short enough to match atomic spacings, X-rays must carry enormous energy. When such high-energy photons strike matter, they can knock electrons out of atoms, ionize them, disrupt bonds, and damage delicate structures. X-rays see atoms, but in seeing them, they often scar them. Scientists needed something gentler, a wave with a wavelength as small as an atom's size, but with much less destructive energy. And that brings us back to electrons. Electrons, when they move, also behave like waves. Their wavelengths shrink as their speeds increase, according to de Broglie's formula. But unlike X-ray photons, electrons with a given wavelength carry far less energy. A 0.1 nanometer X-ray photon is a tiny hammer, dangerous and unforgiving. A 0.1 nanometer electron wave, on the other hand, is more like a soft fingertip passing gently over the structure it probes. This delicate balance, atomic scale resolution without atomic scale violence, is what makes electrons so remarkable. When you accelerate electrons through a few hundred electron volts, their wavelengths become small enough to match atomic distances. Yet the total energy is still modest enough to feel the atoms not scorch them. In a sense, electrons whisper their questions to matter instead of shouting them. This is why electron microscopes became such powerful tools. Using magnetic lenses instead of glass, they can focus electron waves into beams so narrow they thread through atomic lattices like needles through cloth. When those beams pass through or scatter off a sample, their wave patterns hold the imprint of each atom's position. The result is not an image made from reflected light. It is an image made from interference, from the way waves merge, cancel, and reinforce, from the subtle language of probability. Modern transmission electron microscopes can resolve details smaller than 1/10 of a nanometer, small enough to distinguish individual columns of atoms, to watch defects crawl through crystals like slow-moving shadows, to see materials breathe and shift with temperature and stress. Light, for all its beauty, cannot do this. X-rays can but leave scars. Electrons can gently, quietly revealing the hidden geometry of matter without tearing it apart. This inversion of what we expect, light becoming too clumsy, electrons becoming the more refined tool, is one of science's softest surprises. Our eyes evolved for the macroscopic world. We trust light to reveal what's real, but nature is broader than our senses, wider than our instincts. In the atomic realm, photons are too coarse, too energetic. Electrons are the ones with the finer touch. And so, as humanity pressed downward into matter's depths, electrons became our main guide, our subtle eyes in a world too small for light to grasp. They map the architecture beneath biology and chemistry, beneath metal and mineral, beneath the visible and the imaginable. But even electrons with their tuned wavelengths and careful probing can carry us only so far. Beneath atoms lies the nucleus. Beneath the nucleus, new mysteries. And at those scales, our tools must change again, not just because the distances shrink, but because the forces inside atoms become wild and powerful. The next question waits quietly. If atoms have structure and electrons can show it, what about the nucleus itself? Is it solid or hollow? And what lives inside its depths? Rutherford's gold foil and the hollow atom. Imagine a quiet laboratory in 1909. No buzzing electronics, no flashing sensors, just simple tools, dim yellow lamplight and a thin sheet of gold so delicate it trembles at the slightest breath. At the centre of this scene stands Ernest Rutherford, a man with a sharp mind and a curiosity sharpened even further by frustration. For decades, physicists had pictured the atom as a diffuse pudding-like sphere, a soft cloud of positive charge with electrons sprinkled throughout like raisins suspended in dough. It was a comforting image, clean and symmetrical, but Rutherford suspected nature was hiding something deeper. To test it, he needed a projectile. Something small, swift and piercing, yet gentle enough not to tear the gold foil apart. He chose alpha particles, the glowing embers of radioactive decay. Each alpha particle is tiny compared to the width of a human hair, but massive enough to act like a miniature cannonball. Rutherford and his students Hans Geiger and Ernest Marsden prepared a setup so exquisitely delicate that it feels almost surreal by today's standards. They aimed a stream of alpha particles at a sheet of gold foil, only a few hundred atoms thick, so thin it was almost transparent to light. The idea was simple. If the atom were a uniform blob of positive charge, the alpha particles should pass straight through with perhaps a slight nudge. A soft breeze through a fog, nothing dramatic. At first, everything went as expected. Most of the particles sailed forward undisturbed, pinging onto a fluorescent screen placed behind the foil. Their faint flashes formed a constellation of tiny green sparks, each representing a successful passage through the invisible world of atoms. But then the impossible happened. Every so often, very rarely, an alpha particle didn't pass through. It bounced back. A tiny bullet, fired at nearly the speed of light, hit something inside the gold atom and ricocheted almost directly toward the source. It was as if you fired a heavy artillery shell at a sheet of tissue paper and watched it rebound. Rutherford later described this moment with a kind of stunned wonder. It was as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Something inside the atom was hard, extremely hard. Something tiny, dense and concentrated. The pudding model dissolved that day. From these scattered deflections, Rutherford deduced the true structure of the atom. Almost all of its mass is crammed into a nucleus so tiny that if the atom were a cathedral, the nucleus would be a grain of dust floating in its center. The rest, everything else, is empty space. Electrons orbiting at distances so vast relative to their size that the atom becomes almost all void. This realization shifted physics forever. The atom was not a featureless cloud, it was a miniature solar system, mostly empty with a violent, dense heart. Picture it. A nucleus, just 100,000th the width of the atom, holding almost all the atom's mass. It is a speck suspended in a vast, silent chamber. Electrons zip around it in probabilistic clouds like fireflies in a cavern. The scale is so extreme that if the atom were a stadium, the nucleus would be a single insect walking on the 50-yard line. Everything else, the seats, the air, the lights, is empty. We began by looking for structure in matter, and we found emptiness. We found that reality at its smallest scales is mostly nothing. But the new question that rose from this void was even more intriguing. If the atom is hollow, if most of it is space, is the nucleus at its center solid? The gold foil experiment could only tell us so much. It uncovered the existence of the nucleus, but not its internal structure. The energies used in Rutherford's experiment were enough to bounce off the nucleus, not peer into it. It was as though someone threw a pebble at a steel ball. You would know the ball exists, but you would learn nothing about what lies inside it. To probe the nucleus itself to see whether it is solid, hollow, or something strange as scientists would need a new kind of probe. Something far more precise than alpha particles. Something point-like, capable of threading the gaps between proton and neutron surfaces. Something that carries a wavelength short enough to slip inside that dense core. Electrons. But not the gentle electrons used in early microscopes. These would need to be accelerated to enormous energies, billions of electron volts, to shrink their wavelengths to a scale that could challenge the nucleus's interior. And so decades after Rutherford's experiment, an idea began to take shape. If alpha particles gave us the shape of the atom, perhaps high-energy electrons could reveal the shape of the nucleus. This idea eventually grew into one of the largest scientific instruments ever built, a 2-mile-long tunnel on the hills of California, a machine designed to fling electrons at nearly the speed of light, the Stanford Linear Accelerator Center, SLAC, a place where humanity's curiosity met the hidden architecture inside protons and neutrons. The question Rutherford opened, what lies inside the nucleus, was about to be answered. And the answer would reveal not just the structure of matter, but a new layer of reality, quarks, gluons, and the restless storm that lives at the heart of everything, SLAC, and the first glimpse inside protons. Imagine standing at the edge of a perfectly straight tunnel 2 miles long, disappearing into the California hills like a quiet silver thread. There is no roaring engine, no flashing light, just a long, serene line of concrete and steel stretching toward the horizon. Beneath its stillness lies one of the most extraordinary instruments ever built, a machine designed not to break matter apart with brute force, but to illuminate the invisible gears inside reality. This is the Stanford Linear Accelerator Center, SLAC, a straight-line quiet thunderbolt for electrons. Inside that long tunnel, electrons are coaxed, nudged, and finally hurled forward by pulses of radio frequency energy. Each pulse gives them a little more speed, a little more focus, until they skim along just shy of the speed of light. At these energies, tens of billions of electron volts, their wavelengths shrink to unimaginably small scales. Tight, sharp, almost needle-like. It's this transformation that allows electrons to do something miraculous, become probes capable of slipping into the heart of the proton itself. Rutherford had used alpha particles' tiny cannonballs to locate the nucleus. But alpha particles are bulky and fuzzy by quantum standards. They feel the nucleus from the outside like tapping a wall to guess whether it's hollow. Electrons, by contrast, are point-like. As far as our experiments can tell, they have no internal size at all. They behave like perfect mathematical points, infinitely small, sharp and precise. This makes them the ideal tool for asking the next question: is the proton solid, or does it contain something even smaller? To answer this, SLAC scientists used a technique called deep inelastic scattering. The phrase sounds intimidating, but the idea is simple in spirit. You take ultra-energetic electrons, fire them at protons, and watch how they ricochet. Much like shining a flashlight into a dark room and studying the reflections, the way electrons bounce reveals what they struck inside. If the proton were truly a solid ball of charge, the electrons would scatter predictably. Each would glance off the smooth electric field surrounding it, leaving behind a tidy pattern. But when SLAC turned on its beam and recorded the results, something unexpected and quietly electrifying appeared. The electrons were bouncing off hard spots inside the proton. Not a smooth interior, not a uniform cloud of charge, but tiny concentrated points, 3 of them, each deflecting electrons in distinct ways. The scattering angles told a story that no one could ignore. The proton was not fundamental, it was built from smaller components. These hard spots were the first experimental hints of something theorists had already suspected, but could not prove: quarks. Murray Gell-Mann and George Zweig had proposed the idea years earlier, that protons and neutrons were made of 3 quarks each bound together by the strong force. But until SLAC quarks were mathematical conveniences, clever bookkeeping devices to explain patterns in particle physics. Their existence had not been confirmed. SLAC changed that. The electron scattering patterns were unmistakable. Electrons weren't deflecting off a single uniform charge. They were striking a triplet of dense points inside the proton. The proton was composite. This discovery was one of the great turning points in modern physics. Like Rutherford's gold foil experiment had shattered the atomic pudding model, SLAC shattered the notion of the proton as an indivisible brick. What looked like a fundamental particle turned out to be a dynamic cluster of deeper ingredients, quarks, held together by the fierce, almost unbreakable grip of gluons. The deeper we peered, the more structure emerged. Physicists realized they were witnessing something profound, an entire layer of nature hidden beneath the nucleus. A churning, flickering storm of quarks and gluons. A world where the familiar rules of electromagnetism fade and the strong force takes over with almost mythic intensity. As the data came in, the standard model of particle physics began to crystallize. Protons and neutrons, once thought to be the building blocks of matter, were revealed to be composite actors in a far larger and more complex play. The universe was not made from atoms nor from protons and electrons, but from quarks and leptons, deeper, stranger beings moving to the rhythm of quantum fields. And from SLRC onward, a new rule quietly replaced the old one. Even the solid-looking heart of matter is built from something smaller. Electrons firing like tiny lanterns into the darkness of the proton showed us that the structure of the universe continues downward, layer after layer, each one stranger than the last. Now the question deepens. If protons contain quarks, and quarks are held by gluons, what kind of world lives inside that storm? And if we push our gaze even further inward, how long can this journey continue before reality itself pushes back? Quarks, gluons, and the storm inside matter. By the time SLAC revealed the first hints of quarks, physicists had already begun preparing themselves for a strange possibility that inside every proton and neutron, the quiet solidity of matter might dissolve into something far more turbulent, far more alive, something less like a marble and more like a storm. To understand this storm, imagine drifting downward again past the size of atoms, past nuclei and into the trembling heart of a proton. But instead of finding a rigid sphere or a tidy arrangement of smaller particles, you encounter motion, vibration, flickering points that appear and vanish bound together by threads of force that stretch, tighten and snap back with unimaginable strength. These points are quarks, and the threads binding them are gluons, the carriers of the strong nuclear force. At first glance, quarks sound simple. There are 6 types: up, down, charm, strange, top and bottom. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up. But as you settle deeper into this mental landscape, something becomes clear quarks are anything but simple. They come with a special kind of charge, not electric, but more mysterious, known as colour. Colour in this context doesn't mean red, green and blue in a painter's sense. It's a metaphor, a way of describing a type of charge that allows quarks to interact through the strong force. Gluons themselves also carry colour, allowing them to bind quarks together in a constant exchange of energy and identity. Unlike photons, which glide through space without interacting with one another, gluons are self-interacting. They tug on each other, twist around each other and weave a web so tight that quarks cannot escape it. The force they generate is so powerful that quarks have never been found alone, not once. Even in the most energetic collisions humans have created, this phenomenon is called confinement. It means that no matter how hard you try, you cannot pull a single quark free. If you stretch the bond between two quarks, the energy you pump in doesn't tear them apart, it creates new quarks, binding into new particles instead. Nature protects quarks from solitude, and yet a paradox lies at the center of this overwhelming strength. While quarks are tightly confined at normal distances, when they get extremely close, inside the tiniest regions of the proton, they behave almost free. They zip around nearly independently, as if the force binding them momentarily loosens. This behavior, discovered in the early 1970s, is called asymptotic freedom. It means that at very short distances, just fractions of a femtometer quarks glide like skaters on a nearly frictionless rink. But as soon as they drift farther apart, the strong force snaps tight again, like a rubber band that resists stretching more and more with every millimeter. This dual nature, gentle up close, brutal at distance, is one of the great wonders of physics. It is what shapes the proton into something far richer than a ball of three particles. Instead, inside every proton and neutron lives a flickering storm, three valence quarks forming the bare minimum structure, a sea of quark-antiquark pairs popping in and out of existence, gluons swirling in constant exchange, carrying colour back and forth. Fields so intense they generate their own participants. Nothing inside the proton is still. Nothing is solid. Everything is motion and exchange. If you could somehow shrink yourself to a tiny observer within this storm, the world would not appear as particles sitting still in a void. It would feel more like a churning ocean, peaks and valleys of field energy quarks darting like fireflies caught in a web of threads, gluons snapping between them in shimmering arcs. Quantum chromodynamics, QCD, is the theory that describes this world. Its equations predict confinement and asymptotic freedom. Its mathematics maps the way color charges braid quarks and gluons into stable structures. But it also tells us something deeply human, that what seems solid is actually a dance, a blur of relationships rather than simple building blocks. Even the mass of the proton, almost all the mass of the atom, does not come from the quarks themselves. The quarks' actual masses are tiny. Most of the proton's mass comes from the energy of the storm inside it. The field energy, the motion, the binding, it all contributes. Mass at this level is not a quantity but a form of vibration, and the deeper we look, the more energy we need to resolve smaller distances. To peer inside the proton storm, we need probes with wavelengths on the order of 10-18 meters, requiring energies measured not in millions of electron volts, but in billions, even trillions of electron volts. At these scales, beams measured in giga-electron volts, GeV or tera-electron volts, TeV, become our rulers. The shorter the wavelength, the deeper our gaze, but also the more violent the interaction. As energies grow, the storm inside the proton not only becomes visible, it becomes disturbed, sometimes shattered, revealing the rules that hold it together. But even quarks, the restless fundamental players of QCD, do not mark the end of the journey. Because as the energies we use to probe matter grow higher, something else begins to stir. Something not inside the proton but between particles themselves. Gravity. A force so weak at ordinary scales that it barely whispers inside atoms, but so strong at enormous energies that it threatens to collapse our microscopes by curving space itself. Before we reach that limit, our journey must visit the machines that pushed further, smashed harder, and illuminated deeper than ESLAC the great colliders that followed. But for now, one truth stands clear: even the heart of matter is not a solid thing, but a storm alive with motion, color, and energy, colliding worlds, CERN, Fermilab, and learning by smashing. Once SLAC revealed that protons held secrets, quarks and gluons swirling inside like a living storm, the next step was clear: to learn more, we would need even more powerful instruments. Slack's straight 2-mile tunnel had given us our first glimpse of the proton's inner structure. But to map that storm in detail, to watch quarks recoil, gluons multiply, and the very fabric of matter crackle under stress, we would need energies higher than anything ever produced before. This is where the world's great circular colliders entered the story: the Tevatron at Fermilab near Chicago, and the massive ring of CERN beneath the border of France and Switzerland. Unlike SLAC, which fired electrons in a straight line, these colliders use magnetic fields to bend particles into a circular track. Every lap added more energy, like pushing a child on a swing, gentle at first, then harder, then with exhilarating force. Eventually, the protons inside these rings would race around at such speeds that their wavelengths shrank to unimaginably tiny scales, sharp enough to probe structures far smaller than what a SLAC had illuminated. But why collide protons at all? It sounds almost primitive, smashing things together to see what they're made of. But at the smallest scales of nature, smashing is not a gesture of destruction. It is a form of illumination. When two protons collide at nearly the speed of light, their internal quarks and gluons erupt into a burst of energy and new particles. These sprays of fragments, called jets, streak outward in all directions, carrying encoded information about the collision. Physicists read these jets the way a musician might recognize a song from just a few scattered notes. They look at the angles, the spreads, the energies of the particles, and reconstruct what must have happened in that instant of collision. It's a little like striking a bell in the dark and listening to how the sound rings, fades, and echoes to infer the bell's size, shape, and thickness from vibrations alone. In every collision, nature briefly reveals itself. At Fermilab's Tevatron, protons were accelerated to nearly 2 trillion electron-volts energy scales that made Esliker's beams seem almost gentle by comparison. At these energies, the internal storm of quarks and gluons didn't just shimmer, it roared. Collisions created jets that gave us sharper evidence of the strong force, new insights into gluon behavior, and famously the discovery of the top quark in 1995. The top quark is the heaviest fundamental particle we know so heavy, it cannot form stable matter lasting only a microscopic instant before decaying. But its very existence confirmed that the quark family was complete. Meanwhile, across the Atlantic, CERN pushed boundaries with its own machines, first the super proton synchrotron, then the large electron-positron collider, and ultimately something on a scale humans had never attempted before. But before we arrive, let's linger for a moment on what these collisions teach us. At higher energies, the proton becomes less like a solid object and more like a constantly shifting cloud. Quarks inside it share momentum with countless gluons, which split into more quarks and more gluons. The faster you strike a proton, the more volatile this cloud becomes. In deep collisions, it's as if the proton is momentarily stripped of disguise, its internal chaos frozen for just long enough to measure. Physicists noticed something remarkable: as energies increased, the number of gluons inside the proton skyrocketed. A proton at rest contains 3 quarks and a modest gluon C. A proton moving at near light speed is a sunburst of activity, a dense cloud of gluons flickering into and out of being. To probe this storm, colliders had to deliver more energy, more precision, more collisions per second. Each leap forward demanded engineering on a scale that bordered on the impossible colder magnets, more stable beams, deeper vacuums detectors, capable of capturing billions of events without blinking. Eventually, the Tevatron reached its limit, and the torch passed to CERN. Below the green fields outside Geneva lies a circular tunnel, 27 kilometers, 17 miles around. The Large Hadron Collider was built to accelerate protons to energies never before achieved, smashing them together with such intensity that for moments, trillionths of a second, the early universe flickers back into existence. But before we descend into that tunnel, pause here in the glow of the Tevatron and CERN's earlier machines. Think of the jets spraying from collisions, the detectors lighting up like constellations, the patterns whispering stories about quarks, gluons, and fields. Think of how each time humanity managed to push energy higher, nature responded with deeper structure, richer detail, more intricate behavior. And think of the quiet paradox growing beneath all this progress. Every attempt to see smaller requires more energy, but more energy brings us closer to a dangerous frontier, a point where gravity itself begins to interfere. Before we face that frontier, our journey takes us to the grandest collider ever built, a machine that doesn't just study quarks, but shakes the very fields that give particles their mass. The Large Hadron Collider awaits. the LHC, the quiet giant microscope under Europe. If you were to stand in the green fields near Geneva and look out across the quiet landscape, you would see nothing unusual, just rolling grass, a few farmhouses, distant mountains softened by mist. But beneath your feet, following a 27-kilometre loop that crosses the French-Swiss border, lies something unlike anything humans have ever built. A microscope the size of a small country. A calm, circular eye opened not with glass lenses but with superconducting magnets, perfect vacuum and timing so precise it borders on the surreal. This is the Large Hadron Collider, the LHC. Rather than beams of light, it uses protons as its source of vision. Rather than glass, it uses magnetic fields, 1/232 of them, each cooled to 1.9 Kelvin colder than interstellar space. At that temperature, the metal becomes superconducting. Electricity flows without resistance. The magnets hold the beams in perfect arcs, bending them gently around the 27-kilometre ring, again and again each lap, adding more energy, more focus, more sharpness. Two beams travel in opposite directions, like twin rivers running around the same circular path. They never touch, not until the moment we choose to let them collide. It takes hours to bring them up to speed, hours of steady acceleration, small pushes that build and build, until each proton carries an energy of 7 trillion electron volts. 7 TeV each. This is not a number we feel in any everyday sense, but in physics, energy is resolution, energy is clarity, energy is the sharpness of our cosmic eye. At 7 TeV, the wavelength associated with each proton shrinks to about 1/10 of a femtometer, a scale small enough to probe the swirling interior of quarks themselves. For comparison, a proton's radius is about 0.84 femtometers. The LHC's vision, if we can call it that, is not merely seeing the proton from the outside, it is brushing against the deepest vibrations inside it. Every lap around the ring is silent in the human sense, yet thunderous in energy. The beams are so intense that if they ever slipped out of alignment, they could melt tons of steel. So they are guided with extraordinary care, stabilized by feedback systems that correct their position thousands of times per second. Inside this controlled storm of magnetism and motion, the LHC becomes something paradoxical. A giant machine that does not feel mechanical. It feels quiet, steady, almost contemplative. And when those two proton beams are finally brought together, crossing paths inside detectors the size of cathedrals, something deeply unexpected happens. The LHC stops being a tool for studying particles. It becomes a tool for studying fields. Because at 14 TeV7 TeV per beam colliding head-on, the collision energy is enough not just to shatter protons, but to disturb the underlying fields woven through space. The Higgs field, which gives mass to particles, trembles ever so slightly. For an instant, a trillionth of a second, a ripple forms in that field, the Higgs boson. We don't see the Higgs directly. It vanishes too quickly. But the fragments left behind, photons, leptons, jets, light up the detectors like sparks in slow motion. And from their patterns, physicists reconstruct the moment the Higgs briefly existed. It is astonishing to think about a quiet ring beneath the Earth, accelerating protons with frozen magnets, becomes the only instrument in existence capable of shaking the field that shapes the universe itself. The LHC does not shatter reality, it touches it. It presses gently against the boundaries of what we can probe, what we can measure, what space-time itself can endure before gravity begins whispering its warnings. At distances of 1/10 of a femtometer, particles no longer behave like self-contained marbles. The collisions reveal quarks as flashes in a storm gluons, as swirling filaments of energy space, as a restless medium where the strong force knots itself into patterns that can barely be described. It is here within the calm heartbeat of this 27-kilometer machine that we begin to sense the next truth. We're approaching a realm where probing deeper no longer only disturbs matter, it disturbs the fields that define reality. The LHC is more than a collider. It is the world's quietest, most powerful microscope, a circular eye that looks not into atoms or nuclei, but into the foundations of existence. And as we push it closer to its limits, the universe begins to push back, shaking the Higgs field, making mass appear. Imagine for a moment that the universe is filled with something you cannot see, cannot touch, cannot smell. Yet it is there everywhere, in every direction, in every empty corner of space. a field that lies perfectly still, like a calm ocean stretching to infinity. You move through it effortlessly, never noticing its presence, never feeling its resistance. And yet this invisible ocean shapes your very existence. Physicists call it the Higgs field. Every particle you have ever heard of, electrons, quarks, W and Z bosons, moves through this field. Some pass through almost freely, gliding with little resistance. Others push against it and slow down like wading through thick honey. The more a particle interacts with this field, the more mass it gains. Mass is not something particles carry with them like a built-in weight. It is something they acquire by moving through the Higgs field's embrace. It is one of the quietest, most subtle ideas in science. Mass is a conversation between a particle and the universe around it. But how do you study a field you can't touch? You shake it. Hard. At the Large Hadron Collider, when two protons collide at nearly 14 trillion electron volts, the energy compresses into a region smaller than a proton. For an instant, a fleeting whisper-short instant, the Higgs field ripples, and that ripple takes the form of a particle A Higgs boson. It appears, trembles, and vanishes almost instantly into other particles, like a single raindrop hitting the surface of a still lake. This is what the LHC's two giant detectors, ATLAS and CMS, were built to watch for. Not the Higgs boson directly, but its fading footprints, pairs of photons, patterns of leptons, jets of quarks spraying outward in delicate angles. Every second, billions of collisions happen inside the detectors. Almost all of them are ordinary. Almost all dissolve into noise. But on July 4, 2012, the noise revealed a pattern. Both detectors, working completely independently, saw decay paths that matched the long-predicted signature of the Higgs boson, a bump in the data, tiny, but undeniable, exactly where theory said it should be. A ripple in the Higgs field had been recorded not once, but again and again. Years earlier, Peter Higgs, quiet, modest, almost shy, had proposed that such a field might exist. When the discovery was announced, reporters searched for words, scientists applauded, and cameras flashed. And in the crowd, Peter Higgs wiped tears from his eyes. "It's really an incredible thing that it has all come true," he said softly. The Higgs boson was not just a particle. It was the final missing piece of the Standard Model, the framework that describes all known particles and forces except gravity. Its discovery told physicists that the structure they had built, this beautiful, precise mathematical machine, was not an illusion. It was real. The universe truly worked this way. And yet the success came with an uneasy whisper. If the Standard Model is complete, why does so much of the universe remain unknown? Dark matter, dark energy, the nature of neutrinos, the imbalance between matter and antimatter, none of these fit comfortably within the Standard Model's walls. The Higgs boson was proof of the model's power, but also proof of its limitations. A final puzzle piece that revealed the picture was bigger than the frame. And beneath all of that lies a deeper truth. At LHC Energies, we are not just observing the universe. We are recreating conditions from the moment after the Big Bang. In every high-energy collision, the vacuum behaves less like a calm field, and more like it did when the universe was newborn, hot, dense, vibrating with raw potential. The Higgs boson flickers into existence the way it did when matter first formed. The LHC becomes, in its quiet, underground way, a time machine, a window not just into the building blocks of matter, but into the early heartbeat of reality itself. And as we coax these fleeting Higgs ripples from the vacuum, we also move closer to a profound frontier, a place where the energies we use do more than excite particles. They begin to disturb the fabric of space and time, a telescope made of energy and data. If you could shrink yourself down to the size of a proton and drift through the heart of the Large Hadron Collider, you would not see gears or pistons or moving parts. You would see silence, a still vacuum emptier than the space between stars, a ring of frozen magnets humming softly at temperatures colder than the cosmic microwave background. And every so often, two tiny points of light protons rushing toward one another, faster than anything has ever moved on Earth. But the true miracle of the LHC is not the collisions themselves. It's the telescope built around them. Not a telescope of glass and mirrors. A telescope made of energy and data. Every second inside the LHC protons collide billions of times. Most of these crashes produce nothing remarkable, just the usual debris of quarks and gluons, the quantum equivalent of dust. But hidden in the torrent once in every trillion events, something astonishing happens. A rare decay pattern, a flash of light, a pair of leptons flying apart at just the right angles, a whisper of new physics. Catching that whisper is the job of the detectors, Atlas, CMS, Alice and LHCe, each the size of a building, each built in layers like the petals of a mechanical flower. They are not cameras in the ordinary sense. They are vast three-dimensional mosaics of silicon scintillators, lead plates, magnetic coils and superconducting circuits. When a collision occurs, particles burst outward through these layers, leaving faint electrical traces, tiny scars of movement. Those traces are not pictures. They are clues. A charged track here, a spark of energy there, a sudden disappearance where a neutrino must have slipped past unseen. Physicists work backwards from these fragments, reconstructing the invisible moment of collision. It's like watching ice shards scatter across a frozen pond and deducing exactly how the stone must have struck the surface, or like listening to the echoes of a broken bell and inferring its shape from sound alone. But even the most sophisticated detectors in the world cannot handle every collision. The LHC generates petabytes of raw data every second, far more than humanity could ever store, let alone analyze. So the detectors make choices. They decide in microseconds which events are mundane and which might hold secrets. A cascade of algorithms, some written by physicists, some sculpted by machine learning, filters out the noise. Only the collisions with unusual fingerprints survive. These filtered events are shipped out across the planet through the worldwide LHC computing grid, a global network of over 170 computing centers spread across more than 40 countries. In living rooms, offices, server farms, and university labs, computers quietly hum through the night, stitching together the subatomic stories buried in those fragments. No single person sees the whole picture, but together they form a mind distributed across continents that slowly sharpens the universe's smallest details into focus. Thousands of scientists, engineers, programmers, theorists, students contribute their part. A person in India writes code that cleans a data stream. Another in Italy calibrates a magnetic coil. Someone in Brazil analyzes photon pairs. Someone in Canada checks timing systems drifting by nanoseconds. And in Geneva, beneath the quiet hills, the protons continue to circle and collide. There is something quietly moving about it, a global collaboration with no borders, no rivalry, no noise, just a shared desire to see the unseen. And the LHC is not done. Over the coming years, the high-luminosity LHC will arrive a major upgrade that will increase the number of collisions by a factor of 10. More collisions mean more rare events, more precision, more data, more glimpses into subtle behaviors of the Higgs field, quark-gluon dynamics, and perhaps, if nature is generous, a first hint of physics beyond the standard model. Every improvement comes with a deeper view. Every deeper view comes at the cost of more energy, and every added bit of energy pushes us a fraction closer to a fundamental limit. Because as extraordinary as the LHC is, it still plays by one rule. To see smaller, you must use higher energy. At some point, that path leads us to a frontier where energy does more than illuminate matter. It begins to warp space-time itself. A point where observation becomes distortion, where clarity collapses into gravity. And that is the quiet question now forming over the control rooms at CERN. How far can this telescope made of energy and data go before reality pushes back, when gravity strikes back the black hole barrier? For more than a century, physics has followed a simple, elegant rule: to see smaller, you must use higher energy. Shorter wavelengths give finer detail. Higher frequencies sharpen our cosmic microscope. Every innovation from glass lenses to electrons to proton colliders has ridden this rule like a guiding star. But there is a quiet twist hiding inside this principle. A moment where nature gently turns around and pushes back. It begins with Einstein. According to general relativity, energy is not just a number. Energy, no matter its form, curves space-time. A hot stove bends geometry. A flashlight bends geometry. Even a thought, if thoughts carried measurable energy, would bend geometry just unimaginably faintly. So what happens when we concentrate enormous energy into an incredibly tiny region? We distort the very stage on which particles move. At first, the distortion is subtle, too small to notice. But as the energy increases and as we squeeze that energy into a smaller and smaller space to get a better look, the curvature grows. Eventually, it becomes strong enough to affect the very measurement we're trying to make. And then comes the turning point, the moment physicists sometimes call the revenge of gravity. Imagine trying to examine a region of space so tiny that you need a wavelength unimaginably small. To get such a small wavelength, you must use particles with tremendous energy. But that energy itself creates gravity, and as you shrink the region further, the energy density climbs until something profound happens. The region you are trying to observe gains an effective mass. Its gravity becomes strong, and then suddenly it collapses into a microscopic black hole. Your microscope does not simply lose resolution, it erases the very thing you wanted to see. This is the black hole barrier. To understand this gently, imagine trying to focus a beam of light tighter and tighter into a single point. At normal energies, that beam simply illuminates finer details, but at extreme energies far beyond what even the LHC can generate, the gravitational field around that focus point becomes so intense that it traps light itself. A horizon appears, a tiny perfect boundary, a point of no return. The region closes itself off. Nothing that happens inside can escape. Suddenly, the idea of probing a small region loses meaning. There is no longer an inside accessible to you. What was once a window becomes a wall. Physicists describe this threshold in terms of the Schwarzschild radius, the radius within which energy or mass must be compressed to form a black hole. You don't need a star. You don't even need matter. Pure energy will do. The rule is simple. Compress enough energy into a region smaller than its Schwarzschild radius, and that region collapses. Using this gentle logic, nature reveals a surprising truth. There is a smallest meaningful length, a scale where observation becomes impossible, a point where space itself refuses to cooperate. This scale is known as the Planck length. About 1.6 is 10 to 35 meters. If you tried to confine energy into a region smaller than that, the Schwarzschild radius of that energy would be larger than the region itself, meaning the act of measuring forces space-time to collapse. The experiment ends before it begins. There is a quiet elegance to this barrier. It isn't hostile, it isn't violent, it is simply the universe protecting its deepest layer. We can imagine gravity and quantum mechanics like two musicians playing different melodies. At everyday energies, their songs blend without conflict. But at the Planck scale, where wavelengths become tiny and energy density is immense, their melodies clash. The quantum world demands sharper focus. Gravity refuses. One asks to zoom in, the other folds space-time shut. Every high-energy collider we build, every shorter wavelength we use, draws us closer to this boundary. It is the horizon of knowledge itself, not because science is inadequate, but because reality has a built-in limit, a point where the magnifying glass becomes a black hole, and beyond that, we no longer speak of distance or location. We speak of quantum foam uncertainty and the need for a new theory, one uniting gravity with the quantum world. Before we go there, pause here at the threshold, because everything past this point reshapes our understanding of space-time and what it means to see it all. Birth of the Planck, scale and quantum foam. If you trace physics downward past atoms, past nuclei, past quarks and gluons, there comes a point where intuition falters. Our rulers, our measurements, even our metaphors begin to unravel. At these depths, space and time themselves become restless. Distances blur, durations shimmer, geometry loses its smoothness, and the universe begins to look less like a calm fabric and more like something alive. This threshold has a name, the Planck scale. It is not a number discovered in a laboratory. It wasn't measured with an instrument or inferred from a collision. It emerged from pure reasoning, from taking the three most fundamental constants in physics and weaving them together. Those constants are c, the speed of a light, the cosmic speed limit, Planck's constant, the graininess of the quantum world, G. Newton's gravitational constant, the strength of gravity. Individually, they describe different realms, relativity, quantum mechanics, and gravity. But if you combine them not numerically but dimensionally, something extraordinary happens. Their units cancel in just the right way to create natural scales of length, time, and energy. These aren't arbitrary numbers. They are where gravity becomes as strong as quantum mechanics, where the two great pillars of physics collide with equal force. Below these scales, neither theory can dominate. Both must be accounted for simultaneously. But what do these numbers mean? Let's try to feel them. Imagine the proton, already unimaginably small to us, blown up until it is the size of the Earth, a sphere the size of a planet now representing a single proton. In that metaphor, the Planck length would be smaller than a single atom sitting on the surface of that Earth-sized proton. Or imagine slicing a meter stick into 1 trillion pieces, then slicing one of those pieces into 1 trillion pieces, then doing that again, and again, and again, 35 times in total, the final sliver would still be larger than a Planck length. Radiation from the early universe, the sharpest microscopes ever built, the tiniest structures we can resolve, none get us remotely close. The Planck length is not merely tiny, it is beyond physical intuition. So why does nature draw a line there? Because at lengths that small space-time can no longer remain smooth. Just as water looks glassy from afar but turbulent up close, space-time becomes frothy, full of quantum fluctuations. This idea was first vividly described by physicist John Wheeler. He called it quantum foam. At scales near 1035 meters, the geometry of space-time trembles under the dual pressure of quantum uncertainty and gravitational collapse. Distances fluctuate, tiny fleeting curvatures appear and vanish. Minuscule wormholes bubble into existence for a moment, then close again. Space does not sit still, it boils. Imagine space-time as a vast ocean. At human scales, the surface looks calm and solid, but at the Planck scale, zoomed in by 35 orders of magnitude, that surface reveals itself as a storm of tiny waves, bubbles and eddies. Quantum fluctuations so intense that even the concept of location becomes fuzzy. This boiling geometry is what the early universe once looked like. During the first Planck time, the first 1044 seconds after the Big Bang, the universe existed in this state of quantum foam. Temperature, density, curvature, all were extreme beyond imagining. Gravity had not yet separated from the other forces. The Higgs field was not yet stable. Even space-time itself had not settled. Everything familiar distance, direction, causality was still sorting itself out. The Planck era is the earliest chapter of reality, the first heartbeat of existence. We cannot observe it directly. Light did not exist yet. But its influence echoes through the cosmos in subtle ways, in the smoothness of the cosmic microwave background, in the distribution of galaxies, in the balance of fundamental constants, in the seeds of quantum fluctuations that later expanded into stars. It is the hidden preface to the entire universe. The idea of quantum foam may sound chaotic or frightening, but there is a kind of quiet beauty in it. A reminder that beneath every stable surface lies a deeper layer of restless creativity. Even emptiness is active, even nothing churns with potential. And standing here at the edge of the Planck scale, one truth becomes clear. Beyond this limit, the very notions of space and time begin to fail. To go further, we need new theories, new ideas that unify gravity and quantum physics. String theory, loop, quantum gravity, holography, all attempt to describe what lies beneath this roiling foam. But before we explore those possibilities, we must first understand the constraints nature imposes. Because the Planck scale is not only a boundary, it is also a clue that reality is granular, dynamic, alive, and far stranger than anything on the human scale. Cosmic echoes, from Big Bang remnants to the Planck era. There is a quiet symmetry in physics, something almost poetic in the way the universe folds into itself. When we peer into the smallest structures of matter, we are not just zooming inward, we are travelling backward in time. Every deeper layer we uncover whispers an older moment of the cosmos. At atomic scales, we meet processes familiar from the first minutes after the Big Bang, when nuclei stitched themselves together in a brief cosmic furnace. At quark scales, fractions of a femtometer, we enter the first microseconds of the universe, when matter existed as a quark gluon plasma, a hot soup where protons and neutrons had not yet formed. And when we push toward the Planck scale tremendously beyond our reach, we brush against the universe's very first breath, that primordial instant when space-time itself was still deciding what it meant to exist. It is astonishing how the infinitely small echoes the infinitely large. Every time we turn up the energy in a particle collider, we recreate quietly, briefly conditions that haven't existed for billions of years. Quark-gluon plasma formed at CERN's heavy ion collisions mirrors the chaos of the universe when it was less than a microsecond old. Nuclear reactions in stars replicate those first few minutes when hydrogen and helium were born. Neutrinos whisper stories from the first second. Each physical scale is a doorway to a cosmic era. And yet, when we try to listen to the earliest chapters, something strange happens, the universe falls silent. To understand why, imagine the cosmos as a child growing up. Our telescopes can photograph the universe when it was a toddler, a small child, even an infant but never a newborn. Light itself becomes the barrier. After the Big Bang, the universe was dense, hot, and glowing with a kind of radiant fog. Photons couldn't travel freely. They scattered endlessly off electrons, never making it far before colliding again. The cosmos was bright but opaque. Only when the universe cooled enough about 380,000 years after the beginning did electrons settle into atoms and light was finally allowed to travel unhindered. This released the cosmic microwave background, the oldest light in existence. That light is our photograph of the young universe, not as an infant but as a baby finally opening its eyes. Our best maps of this ancient glow come from 3 great observatories: COBE 1989, the first to detect the faint ripples in temperature; the map 2001, sharpening the image, revealing delicate fluctuations; Planck 2009, giving us the clearest map ever made of the early cosmos. Together they showed us a universe that was astonishingly smooth, with tiny temperature variations just 1 part in 100,000 that would later grow into galaxies, stars, and the structures we see today. These satellites gave humanity a kind of cosmic birth certificate, but even they could not see beyond that light-filled horizon. They revealed the cradle, not the moment of birth. Everything earlier, those first hundreds of thousands of years, is hidden from direct observation. Not because we lack technology, but because no light from that era can ever reach us. The universe simply wasn't transparent yet. And beyond that, beneath the first second, the first millisecond, the first microsecond, the veil thickens. We can infer, simulate, reconstruct, but not observe. The Planck era is different still. In the first 1044 seconds, the universe wasn't just hot, it was undefined. Geometry quivered, time jittered, space swelled and contracted in violent quantum fluctuations. The 4 forces of nature were fused. Particles existed only as potentials, as possibilities waiting to crystallize. The Planck scale isn't just the beginning of time, it is the boundary between physics as we know it and something deeper. COBE ISOSA map and the Planck satellite give us the earliest image of the universe's surface, a kind of cosmic fossil. But the Planck era is the bedrock beneath that fossil, buried too deep for any telescope to uncover, because no signal, no photon, no neutrino, no gravitational wave has survived from that moment. And yet we chase it. Not with light, but with logic. Not with telescopes, but with equations. Not by looking outward, but by diving inward to the smallest distances, the highest energies, the shortest times. Every collider, every microscope, every calculation that pushes deeper into matter is also a step deeper into the past. Atoms echo the early minutes. Nuclei echo the first seconds. Quarks echo the first microseconds. Fields echo the first instants. And the Planck scale, the smallest scale of all, is the shadow of the very beginning. In that sense, probing small distances is not merely an act of measurement, it is an act of remembrance, a quiet tracing of cosmic history written into the architecture of matter itself. But to move beyond the relics of the cosmic microwave background to approach the Planck epoch more directly, physics must do something bold. It must unify quantum mechanics and gravity. Because only then can we understand the origin of space-time and the strange, restless quantum foam that once filled everything, when uncertainty meets gravity, the gup. For a long time, the smallest scales of nature were governed by a single simple rule, one of the most delicate ideas in all of physics, Heisenberg's uncertainty principle. It says in essence that the universe will not allow us to know everything about a particle at once. If we try to pin down where something is, we lose track of how fast it's moving. If we measure its momentum precisely, its position dissolves into blur. The idea is not a limitation of our instruments, it is a limitation of reality itself. To make this gentle, imagine watching a tiny boat bobbing on a dark lake. If you shine a soft lantern on it, you can see its position, but the light barely pushes on it. If you shine a bright spotlight, the glare is clearer, but the force of the brighter light nudges the boat and disturbs its motion. The more precisely you illuminate its location, the more you disrupt what it's doing. Quantum mechanics works the same way. Photons, the particles of light we use to see, carry momentum. Shine higher energy, shorter wavelength photons onto a particle, and you can locate it more precisely. But the act of looking kicks it harder, scrambling the information you hope to preserve. Heisenberg wrote this mathematically, but the soul of the idea is simple. Nature hides her smallest secrets behind a veil of uncertainty. For decades, this principle guided our understanding of limits. The smaller the region you wanted to poke into, the shorter the wavelength you needed. The shorter the wavelength, the higher the energy. The higher the energy, the finer your resolution. But something strange happens when we push this logic toward the Planck scale. Something new enters the picture: gravity. At low energies, gravity is so weak compared to quantum effects that we usually ignore it. But as we keep increasing the energy of the probing photon, shrinking its wavelength, sharpening our measurement, the energy becomes so large that it begins to bend space-time itself. Imagine trying to locate a particle by firing an unimaginably energetic photon at it. The photon is so concentrated, so intense, that its energy creates a tiny gravitational well. The region you are probing no longer sits on a calm, stable sheet of space. Instead, the sheet bends, curves, warps. The photon no longer merely illuminates the particle, it distorts the stage the particle sits on. At first, the distortion is mild, but as you increase energy further, trying to see even more sharply, the gravitational dent deepens. At extreme energies, the probing photon threatens to create a microscopic black hole. Your attempt to zoom in doesn't clarify the picture, it destroys it. This leads physicists to an elegant conclusion known as the generalized uncertainty principle, or GUP. The ordinary uncertainty principle says smaller position uncertainty, more momentum uncertainty, and more momentum, more energy. But the GUP adds gravity to the equation, and with gravity included, the relationship changes shape. At first, increasing energy does reduce the uncertainty in position, just as in standard quantum mechanics. The blur shrinks. The world comes into sharper and sharper focus, but only up to a point. Beyond a certain threshold, when energy density becomes strong enough to curve space-time, the position uncertainty reaches a minimum and then begins to grow again. Push harder and things get blurrier. Increase energy and you lose information. Try to see more clearly and the picture dissolves. This minimum positional fuzziness, this limit below, which space refuses to be resolved, is essentially the Planck length. It marks the boundary between a world where space is smooth enough to talk about locations and a world where the very idea of location stops making sense. Imagine trying to measure the height of a wave on the surface of a boiling kettle. At a certain scale, the surface isn't smooth enough to speak of waves at all, it's just turbulence. The Planck length is the turbulent scale of space-time. The GUP tells us that space-time is not infinitely divisible. There is no ultimate microscope, no final zoom, no perfect resolution. The universe is not built like an infinitely detailed painting. It is built like a mosaic. The tiles are incredibly tiny, so tiny that we will never see them directly, but they are there. And the act of trying to zoom further only shakes the mosaic apart. This marriage of uncertainty and gravity is more than a mathematical curiosity. It is a signpost. It tells us that quantum mechanics and general relativity are whispering the same message. At the Planck scale, neither theory is complete alone. A new framework must emerge, one that unites them. String theory, loop quantum gravity, holography, all are attempts to answer the question that GUP quietly raises. What is space made of, and what happens when the tools we use to measure reality begin to alter reality itself? Before we explore these possible answers, pause here, because the GUP marks the moment when physics stops being about objects in space and becomes a study of space itself. Information, black holes, and holographic pixels. By now, our journey has taken us to the threshold of the Planck scale, the place where distances dissolve, space-time trembles, and uncertainty refuses to shrink any further. Here, gravity and quantum mechanics speak with equal volume. Here, microscopes collapse into black holes and the very notion of location becomes blurred. But something even stranger waits at this boundary. Not a particle, not a field, but information. It turns out that the fabric of the universe may not be built from matter or energy alone, but from bits, fundamental units of information, encoded in the geometry of space itself. To see how we get there, let's start with a gentle idea. If there is a minimum length, a smallest meaningful scale, the Planck length, then space-time is not a smooth continuum. It is pixelated. Not in a digital sense, but in a deeper physical one. Just as images on a screen cannot contain more detail than the number of pixels they're made from, the universe cannot pack infinite detail into a finite region. There are limits. Limits enforced by quantum mechanics, and limits enforced by gravity. Black holes reveal this boundary with clarity no other object can match. In the 1970s, Jacob Bekenstein wondered, how much information can you store inside a region of space? If you compress matter into a smaller and smaller region, The information it contains increases, but gravity sets an ultimate limit. Compress enough matter and you form a black hole. And so Bekenstein asked, what is the maximum possible information a black hole can contain? Stephen Hawking soon discovered something astonishing. A black hole is not featureless. It is not an empty, silent void. It has temperature, it radiates, and it has entropy, a measure of the amount of information hidden behind its horizon. That entropy, called the Bekenstein-Hawking entropy, is proportional not to the volume of the black hole but to its surface area. Every Planck-sized area on the horizon contributes exactly one basic unit of entropy. This is one of the deepest discoveries in all of physics. It means the information content of a black hole is proportional to the number of Planck-sized pixels on its surface. Not the space inside, not its volume, its boundary. The inside of a black hole could be vast, but the information describing it is encoded on a thin two-dimensional surface. This idea quietly upends our intuitions. We're used to thinking of reality as volumetric, three-dimensional, continuous. But black holes insist that the deepest accounting of information happens on surfaces in Planck-scale tiles of area, not in volumes. It is as if the universe, or at least its most extreme objects, stores information the way a hologram does. And from that idea grew one of the most revolutionary proposals in theoretical physics, the holographic principle. It suggests gently but firmly that a region of space can be completely described by information encoded on its boundary. A three-dimensional world arising from a two-dimensional screen of Planck-sized bits. The holographic principle does not say the universe is an illusion. It says the universe may be more economical than we imagine. The richness of three-dimensional physics may emerge from deeper bookkeeping on a two-dimensional surface, like a hologram etched on a plate where each tiny part holds information about the whole. If the principle is correct, then the idea of volume becomes secondary. Space inside a region is not where the information lives. Information clings to the edges. Distances, locations, volumes, these become emergent concepts, built from the patterns encoded on those Planck-sized boundary pixels. Reality becomes a kind of projection, not in the philosophical sense, but in the geometric one. And this ties back to the Planck scale beautifully. Each Planck area acts like a fundamental pixel, a smallest possible unit of information, a limit that nature will not subdivide. Beyond that scale, space-time stops behaving like a smooth sheet and becomes a mosaic of information-bearing tiles. Everything we see, from quarks to galaxies, may arise from the ways these tiny surface pixels interact, fluctuate, and weave patterns into higher dimensional shapes. It is a soft, quiet, humbling idea that our three-dimensional world is a kind of shimmering image emerging from information scribbled on its boundaries. That black holes, the darkest objects in the universe, shine brightest when it comes to telling us what space is made of. That the limits imposed by quantum mechanics and gravity, uncertainty and collapse are not obstacles, but clues. Clues that the universe is at its heart an information processing engine. Clues that the Planck length is not just a distance but a pixel size. Clues that every surface hides a deeper code. And as we move forward towards string theory, loop quantum gravity, and other attempts to describe this code, we find ourselves asking a profound question. If our universe is written in Planck-scale pixels, who or what does the writing "strings when points become vibrations"? By now, every step we've taken toward the Planck scale has led us deeper into a paradox. The closer we try to look, the more violently space-time reacts. Our microscopes collapse into black holes. Uncertainty stops shrinking and begins to swell. Geometry itself flickers into foam. Gravity and quantum mechanics, usually quiet neighbors, begin to shout over one another. At this boundary, the idea of a point particle, a particle with no size, no structure, no dimensions, becomes impossible to sustain. Points cause trouble. Infinite trouble. If you imagine all of a particle's properties crammed into a dimensionless point and then subject that point to enormous energy, the mathematics quickly breaks down. The forces grow infinite. The curvature grows infinite. Everything blows up in a storm of infinities that no equation can tame. For decades, physicists struggled to understand why nature should behave so badly at the smallest scales. And then in the late 20th century, a radically different idea emerged, quiet at first, then spreading across the landscape of theoretical physics like a new melody. What if particles are not points at all? What if they are strings? Not strings in the ordinary sense, but unimaginably tiny filaments about the size of the Planck length, looping and vibrating in multiple dimensions. If you try to compress a string, you don't get a smaller point, you get tension, and when the tension rises enough, the string stretches instead of collapsing. Suddenly the infinities vanish, the equations calm down, gravity stops diverging, quantum mechanics stops raging. A string cannot be compressed below the Planck scale. It is already that small. This single change, replacing points with one-dimensional loops, smooths out the violent behavior of particles at ultra-high energies. Instead of a point absorbing energy with no resistance, a string begins to vibrate in richer, higher modes. Energy no longer sharpens detail. It enriches the vibration. In this picture, an electron is a string vibrating in one pattern. A photon is the same string vibrating in another. A quark is yet another vibration. Every fundamental particle becomes a musical note, a resonance of the same underlying object. This is not a metaphor. It is the mathematics of string theory itself, and among all the vibrational modes, one stands out. A mode that behaves exactly like the graviton, the hypothetical quantum of the gravitational field. String theory didn't set out to explain gravity. Gravity simply fell out of the equations, an automatic consequence of allowing strings to vibrate. As if nature was saying, if you want a consistent quantum picture of the universe, gravity must be here. Brian Greene often describes the universe as a cosmic symphony, and Edward Witten speaks of physics as the study of vibrating elemental filaments. In their view, and in the view of string theory, matter is not built from tiny marbles but from tiny tremors. Reality becomes music. Every particle becomes a tone, and this changes our view of resolution forever. At normal energies, strings appear point-like because their length is so tiny, 10 billion times smaller than a nucleus. But as you probe deeper, pushing energies higher and wavelengths shorter, you do not see new inner details. You do not find smaller constituents. Instead, the string stretches. Your added energy is absorbed not into shrinking the object but into exciting new modes of vibration. The harder you try to zoom in, the more the string swells, dances, and complicates its patterns. At the extreme zoom of the Planck scale, your microscope does not reveal smaller structure. It reveals more complex motion. The universe becomes dynamic rather than granular, expressive rather than finely cut. Point particles break the mathematics. Strings keep the mathematics smooth. Points collapse into black holes. Strings resist collapse by vibrating more intensely. Points offer no structure to absorb energy. Strings offer infinite room for new modes. And perhaps most beautifully, points give us the illusion of separateness, while strings give us the possibility of unity. That unity is this: all particles are different vibrations of the same fundamental object. The universe is made not of things, but of patterns. With strings, the Planck scale is no longer a hard edge. It becomes a soft boundary, a place where the character of physics changes, where energy reshapes objects instead of revealing smaller bits. But strings do not live in ordinary space. They require extra dimensions curled up so tightly we never notice them. To explore those dimensions, we must move deeper still into a world where geometry and information intertwine. Before we go there, pause here. You're standing at the edge of a universe made of vibrations, a world where the music of strings replaces the granularity of points, and where the limits of measurement transform into the choreography of motion. From here we step into theories that do not merely modify space-time but build it from something deeper. Hidden dimensions and the string landscape. If strings are the vibrating threads that weave reality, then they need something to vibrate in. A violin string needs air to carry its sound. A guitar string needs a wooden body to shape its tone. And in string theory, the body that shapes each vibration is space itself, not just the 3 dimensions we move through, but dimensions we cannot see. String theory requires more dimensions than our eyes or instruments can detect, not as an optional flourish, but as a mathematical necessity. Depending on the version, the universe contains 10 dimensions in superstring theory, 11 dimensions in M theory, the grander framework that embraces all 5 string theories. We experience only 4, 3 of space, 1 of time, because the others are curled up so tightly, so delicately, that they slip past our senses entirely. Imagine a drinking straw. From far away it looks like a one-dimensional line, but up close you see it has a small circular dimension wrapped around it. To an ant walking on the straw, both dimensions are real. To us, the circular one is invisible. The extra dimensions of string theory are like that, only far smaller. far more intricate, far more alive with geometry. According to the theory, these hidden dimensions fold themselves into complex shapes called Calabi-Yau manifolds. These are not simple spheres or tori, but elaborate multi-dimensional origami surfaces with handles, curves, twists, and symmetries far beyond everyday intuition. Though invisible, they are not irrelevant. Their geometry controls everything. In this picture, the particles and forces we observe, electrons, quarks, photons, the Higgs, the strong and weak and electromagnetic forces, are all determined by the shape of these hidden spaces. Strings vibrate differently depending on how the extra dimensions are curled. Slight changes in geometry alter the resonant patterns, changing which particles exist, their masses, their charges, the strengths of forces, and even the number of particle families. The universe we inhabit is not the only one string theory allows. It is simply one particular arrangement of extra-dimensional geometry. A single chord played on a vast and intricate instrument. And here gently string theory reveals something astonishing. There isn't just one Calabi-Yau shape. There are many, possibly unimaginably many. Physicists sometimes speak of the string landscape, the enormous space of all possible extra-dimensional shapes and configurations. Each shape corresponds to a different consistent universe with its own particles, its own forces, its own physics. Some landscapes may have no electrons, some may have no gravity, some may have wildly different constants of nature. Some might have dimensional structures so alien that the word particle means nothing there. How many such universes does the landscape contain? Current estimates suggest numbers like 10^500, a number so large it strains the meaning of counting, a space of possibilities so vast it dwarfs not only our universe, but our imagination, and yet we find ourselves in one of them, a universe, with precisely the right mix of ingredients to make stars, chemistry, planets, oceans, and life. Not through intention or necessity, but because this is the geometry we happen to inhabit. This idea is sometimes portrayed as controversial, but we need not see it that way. Instead of thinking of the landscape as a problem, we can see it as a source of wonder. Nature may not be limited to one way of existing. Perhaps the laws we see are not the only laws that can be. Perhaps the deep symphony of strings plays not one melody, but countless ones, most unheard, some harmonious, some discordant, all part of a grander possibility space. And in that view, our universe is a tiny island in a vast archipelago of potential realities, a single delicate expression inside a far greater mathematical ocean. The hidden dimensions beneath us do not make us small. They make the cosmos vast, subtle, full of creative potential. And now we face the next question. If extra dimensions shape the vibrations of strings, and if those vibrations create the particles that build reality, then what shapes space itself? What causes geometry hidden or visible to emerge at all? To answer that, we must step beyond strings into something even more radical. The idea that space-time itself might be woven from relationships loops or holographic entanglement. Loops, spin networks, and the grain of space string theory offers one vision of the Planck scale world, a universe woven from tiny vibrating filaments unfolding through hidden dimensions. But there is another vision, quieter, more austere, and profoundly geometric. A vision that asks, what if space-time itself is quantized? Not the particles inside space-time, but space-time itself. This idea leads us into the world of loop quantum gravity, or LQG. Instead of imagining strings vibrating in many dimensions, LQG starts from a simpler question. If quantum mechanics applies to everything, shouldn't it apply to geometry too? In Einstein's theory, space-time is a smooth, continuous fabric. Curvature tells matter how to move, matter tells space-time how to curve. Gravity is geometry, not force. But at the Planck scale, smoothness breaks down. Quantum mechanics insist that nothing, no field, no energy, no measurement can remain infinitely divisible. So LQG takes the bold step, it quantizes space-time itself. In this picture, space is not a continuous expanse but a mosaic, not a fabric but a network, a web of tiny indivisible chunks of area and volume. These chunks are built from structures called spin networks. A spin network is like a cosmic graph. Nodes represent tiny quanta of volume. Links between nodes represent quanta of area. Together they form an intricate lattice not in three-dimensional space but as three-dimensional space. The geometry we experience emerges from how these nodes and links connect, stretch, and intersect. Each node carries a quantum state of volume. Each link carries a quantum state of area. Space is literally knitted from these threads. There is no underlying grid sitting beneath the network. The network is the grid. The network is the geometry. The network is space-time. This view is startling at first, but also elegant. It mirrors how matter is quantized in atoms, energy and photons, electric charge in electrons. Now area and volume join the list of quantized entities. From afar, billions of times larger than the Planck scale, these discrete grains blur together. We do not see the individual nodes or links. Instead, we see the smooth curvature of Einstein's space-time, just as a forest looks smooth green from the sky. While close up it is made of individual leaves. LQG tells us Einstein was right at large scales, but nature becomes granular at its foundations. This granular structure avoids many of the infinities that plague standard gravity. In classical general relativity, if you compress matter enough, the curvature becomes infinite. A singularity forms at black hole centers at the moment of the Big Bang, a place where the equations stop making sense. But in loop quantum gravity, space cannot be compressed arbitrarily. Just as matter cannot be compressed beyond the Pauli exclusion principle, space-time cannot be compressed beyond the smallest quantum of volume. There is a minimum grain size for space. Below that, compression simply cannot occur. And this leads to one of LQG's most striking predictions. The Big Bang was not the beginning. It was a transition. Instead of a singularity where density becomes infinite, LQG predicts a big bounce. As the universe collapses toward what classical physics would call a singularity, the quantum geometry pushes back. The grains of space resist further compression. Gravity becomes repulsive at ultra-high densities. The universe contracts, halts, and then rebounds into expansion. The Big Bang becomes the moment of rebound, not creation. Space and time continue through it, changing phase like water freezing into ice and then melting again. This vision dissolves the singularity problem naturally without extra dimensions or exotic new objects. It is a universe where the quantum nature of geometry protects reality from infinities. A universe where the smooth space-time we experience is a large-scale illusion woven from microscopic loops. And intriguingly, LQG suggests that time itself may be emergent, arising from how the network evolves, not from a continuous background clock. The universe becomes a kind of quantum conversation among nodes and links with geometry itself as the dialogue. In this picture, space is granular. Volume is quantized. Areas come in discrete units. Singularities evaporate. The universe bounces instead of beginning. Loop quantum gravity is not the only attempt to unify quantum mechanics and gravity. But it is one of the few that begins with the idea that space-time is not something we live in. Space-time is something that lives inside the quantum world. And as we step deeper into these ideas, we move toward frameworks where even the notion of space-time dissolves, replaced by something stranger. Still the idea that geometry itself may emerge from patterns of quantum entanglement. Emergent space when entanglement draws the map. For centuries, space has been the stage on which physics plays out. The backdrop, the container, the silent emptiness that holds everything else. We learn to think of objects in space fields on space, and particles moving through space. Even the more elaborate visions of strings and loops still assumed that space-time in some form was the canvas on which everything else was painted. But what if this is backwards? What if space is not the stage, but the story? What if space-time is not fundamental at all, but something that emerges from the way quantum information is shared among the basic constituents of reality? This is the quiet, radical idea taking shape in modern theoretical physics. Space-time may arise from quantum entanglement. Entanglement is the deep, strange connection between quantum systems that allows them to share information instantaneously, regardless of distance. It is not communication, it is not a signal. It is simply a correlation that exists beyond space, an invisible thread connecting particles in a way that defies classical logic. In everyday quantum experiments, entanglement shows up as mysterious coordination. But on a deeper level, it might be the very fabric from which geometry is stitched. Imagine you have a huge network of quantum bits, not bits in a computer, but fundamental degrees of freedom in the universe's deepest layer. These bits can become entangled with one another, forming a web of relationships. Now imagine measuring the entanglement between each pair of nodes. If two nodes are strongly entangled, they are close. If they are weakly entangled, they are far apart. If there is no entanglement, they may not be connected at all. In this picture, distance is not something you define by coordinates, it is something you infer from patterns of quantum information. Space-time becomes a map drawn by entanglement. The closer two regions of space appear, the more entangled their underlying quantum states are. The more entanglement you remove, the more the geometry stretches, thins, and eventually tears. Black holes, wormholes, horizons, these become features not of curved space but of patterns of quantum connectivity. This idea is still young, still tender, still being explored. But its intuitive power is enormous. It suggests that what we think of as here and there, near and far, are not fundamental concepts. They are consequences, a kind of quantum bookkeeping that arises when vast webs of entangled states organize themselves into something smooth and geometric. Nima Arkani Hamed likes to say, space-time is doomed, not as a threat but as an invitation to imagine a deeper layer beneath it, a layer where there is no geometry, no distance, no location, only relationships, only correlations, only structure in the space of possibilities, and from those relationships space itself condenses like dew forming from unseen moisture. In this view, strings are vibrations that live on emergent space. Loops are networks that represent emergent space, but entanglement may be what creates space to begin with. This is a universe not built from things in space, but from relationships that create space as a side effect. Imagine a symphony with no auditorium, only the relationships between notes giving listeners the sense of a hall. Or imagine a spiderweb where the threads themselves define the shape, not the empty air around them. Entanglement draws connections. Connections define adjacency. Adjacency becomes geometry. Geometry becomes space-time. And as strange as it feels, this view unites much of what we've seen. The Planck scale acts like a fundamental pixel size because information can't be subdivided endlessly. The holographic principle emerges naturally if geometry comes from entanglement, then surfaces, boundaries between regions are natural places where information lives. Black hole entropy becomes a count of how many entangled links stretch across a horizon. String vibrations become modes of a deeper informational structure. Loop quantum gravity's spin networks begin to look like entanglement graphs rendered geometric. In all of these information, quantum information quietly animates what we call the universe, and so the question shifts. Instead of asking what the world is made of, we begin asking how the world is related. Space becomes the harmony of entanglement. Time becomes the rhythm of changes in those relationships. The universe becomes a conversation, not a container. This is not the final word. It is not a finished theory. But it is a new way of thinking, soft, profound, and strangely comforting, that the place we inhabit, the space we move through, may be nothing more or less than the shape of connection. When distance melts the natural edge of knowing, you live in a world where distance feels reliable, where time ticks steadily, where locations behave themselves. Every day, without thinking about it, you trust these ideas. Your phone uses GPS, triangulating your position from satellites by measuring how long it takes for tiny pulses of light to reach you. Astronomers point telescopes toward galaxies millions of light years away, confident that distances across space behave in consistent, predictable ways. Engineers at CERN steer proton beams to collide within a fraction of a millimeter, trusting that space-time will not suddenly shift beneath their instruments. On human scales, space and time are solid ground, a gentle floor beneath your feet. But the deeper you follow physics toward the Planck scale, the more that ground softens. The straight lines begin to ripple, the familiar grid dissolves, and eventually at the edge of the very small distance melts. Two paths lead to this same quiet dissolution. The first comes from gravity. You learned that to see smaller you must use more energy, shorter wavelengths, more powerful probes, but concentrate enough energy into a tiny region and space-time curves in response. Push even harder and that region collapses into a microscopic black hole. Your attempt to measure creates an object that hides the very information you sought. Gravity closes the window. The second path comes from quantum uncertainty. Try to trap a particle in a smaller region, and the quantum fluctuations in its momentum explode. Push harder, use higher energy photons to improve your resolution, and those photons begin to distort space-time themselves. Eventually, the more energy you use to measure, the less certain the measurement becomes. Precision reverses its direction. Quantum mechanics closes the window. These two limits, one born of gravity, the other of quantum behavior, meet perfectly at the Planck scale. A length so small it defies comparison. A time so brief, it makes all other durations feel eternal. a boundary where the very concepts of here and there stop behaving like themselves. It is as if nature placed a soft frame around the smallest possible scales and whispered, "You may look closely, but you cannot look infinitely closely. Not because you are limited, but because the universe is wise. This boundary is not a failure of science, it is a feature of reality, a safeguard." Imagine a world where distance could shrink to nothing, where energy densities could rise without limit, where quantum fluctuations had no boundary. Such a universe would tear itself apart instantly. No star would form, no atom would hold, no chemistry, no biology, no consciousness. The limits we find, the Planck length, the Planck time, the curvature threshold where black holes form the quantum fuzziness that refuses to vanish, are all part of a cosmic stability mechanism, a way for the universe to protect its own structure, a built-in guardrail, and yet even though we cannot cross the Planck threshold, we can look for traces of it, hints, whispers in the data. Future detectors of gravitational waves may catch subtle distortions, tiny mismatches between frequencies that hint at a granular texture beneath space-time. Precision measurements of the cosmic microwave background may find minute patterns that reflect geometry from the universe's earliest quantum phase. Experiments in quantum optics, atomic clocks and interferometers may reveal faint signatures, small deviations from smoothness, that betray the existence of an underlying grain. Not enough to break the mystery, just enough to illuminate its edges. You may never see a Planck-sized grain. No telescope can reveal it. No collider can touch it. No microscope can focus that sharply, but you can sense its presence in the way singularities soften, in the way uncertainty bends back on itself, in the way gravity and quantum mechanics both insist on the same limit. In the end, this natural edge of knowing is not a wall, it is a horizon, a gentle reminder that the universe is not infinite resolution, but infinite wonder, that some boundaries exist not to confine us, but to make reality coherent, stable, and beautiful. That understanding the world does not always mean piercing every veil. Sometimes it means knowing where the veils must remain. And standing here at the soft boundary of distance and meaning, your view of the universe becomes clearer, not dimmer, because you now see that the mysteries are not obstacles, they are architecture, a soft good night from the edge of reality. You've travelled a long way tonight, from the gentle glow of glass lenses to the cold hum of superconducting magnets deep under Europe, from electrons behaving like waves to quarks flickering like storms, from the steady logic of microscopes to the violent shimmer of particle collisions, from the calm, predictable geometry of everyday space to the trembling quantum foam beneath it, from strings vibrating in hidden dimensions to loops knitting quanta of volume, from entanglement weaving geometry to the soft boundary where distance dissolves. You have followed the trail of inquiry all the way to the Planck scale, the quiet frontier where gravity and quantum mechanics press against each other, where our tools reach their limit, and where space-time itself begins to breathe with uncertainty. And now at the edge of what can be known, you pause, not because the story ends here, but because this is where the story becomes something gentler, something no longer about seeing sharply, but about feeling the shape of a mystery that doesn't need to be conquered. All along this journey, a theme has followed us like a soft refrain. The smaller we look, the stranger things become. Electrons diffract, photons kick, protons swirl with quarks and gluons, black holes hide information on their surfaces, space-time grains shimmer with loops and spins, geometry emerges from entanglement like a whisper of connection, and the notion of where itself melts into something relational rather than absolute. At the deepest level, the universe may not be made of things at all. It may be made of relationships, patterns, entanglement, stories written in the language of possibility. Everything you've explored tonight, the microscopes, the collisions, the theories, are just tools we use to tell better stories. Not perfect stories, not final stories, but stories that touch however softly the vibrating heart of reality. And the truth is, we may never see a perfectly sharp picture. We may never peel back every layer. We may never stand on the far side of the Planck wall, but that's okay, because the value lies not only in the destination, but in the curiosity that carries you forward, the quiet wonder that draws you from one idea to the next, the sense of companionship you feel with the scientists, thinkers and dreamers who spent their lives leaning into the unknown. And the fact that you're here tonight listening to this means you share that curiosity too. Before we end, let me speak to you directly. If you've enjoyed this journey, I'd be grateful if you gently tapped like or subscribed, or even left a quiet note in the comments, perhaps telling me where in the world you're listening from. Each message is like a tiny point of light in the dark, a reminder that even in our own quiet corners of the night, we're part of a larger constellation of curious minds. But for now, let the questions rest, let the theories dim, let the cosmic foam settle back into silence. You've travelled far enough for one night. Breathe softly, let your thoughts drift. Let your body grow heavy with rest. The universe will still be here in the morning, patient, mysterious, woven from uncertainty, and always ready to reveal a little more whenever you return to it. For now, close your eyes. Let the cosmos fade to darkness. Let curiosity stay awake quietly, glowing in the background as you drift gently into sleep. Good night from the edge of reality.